All right, so last time we introduced this notion, the introduction to what I called the architecture of space-time, which is a pretty grand way of saying it, but basically what I'm trying to get at is that space-time is a mathematical concept, right? Every point in the universe having a set of four identifiers, coordinates, right, which we decided were going to be x0, x1, x2, and x3. And this first one is going to essentially be what we call time, and then these are going to be related to space, as we'll eventually see. But regardless, everything when I say the universe, I mean the whole history of the universe, the future history and the past history, because of this time coordinate. It could, every point that's ever happened or ever will happen has these four numbers. And when I talk about the architecture of space-time, well, that's almost good enough, right? If you kind of think of these coordinate axes as a way of locating every point in space-time, knowing that for the purposes of this work we have to suppress one spatial dimension and remember that the clock time is also part of it. And we think that every spot could actually be named. This is all very abstract, of course, because it's impractical to do so. But ultimately, this is what I mean by the mathematical architecture of space-time. We're starting with this idea that all of space-time can be put into a coordinate system, and that's not so much the architecture. That's almost just like a description of space-time. It's kind of like calling a building, identifying the structure of a building by its color. That's not going to do. We need a lot more to give something what we would call architecture. And although this just labels all the points by name, and that's all it does, it just names every point, we're also going to add this very, very important piece of information at every single point, and that's what we've been working on up to these last few lectures. We're going to give every point in space-time its own vector space, its four-dimensional vector space, it's a real vector space, and each of those vector spaces has this basis of differential operators, where the differential operator is differentiation of unspecified function relative to these coordinates. So some hypothetical functions can exist in space-time, or can exist over space-time, where basically you plug in the location in space-time and this thing gives you some number, right? And the basis of these vector spaces is just going to be these differential operators as described here. It's kind of hard to see why that would be useful or why that would be a good idea. But soon we'll get the sense of why that is the case. That's one of our, once you understand why that is the case, you'll feel like you've made a lot of progress here, because there's a good reason for choosing differential operators to be the basis of our vector spaces. But I haven't emphasized the point that a vector space of that nature is created at every single point in space-time, and they all have their own. And I can name them all V, but it doesn't mean much unless you apply to the V some kind of indication of what point you're dealing with, right? So this would be the vector space at P, the vector space at Q, the vector space at R. And I don't feel like it's belaboring the point to emphasize again that if I take a vector out of Vs, now that vector is going to look like, if it's an arbitrary vector, A mu partial mu, because now this is replacing what we used to call E mu, but we've got a realization. This is totally abstract. So we've realized it by finding a mathematical object that fits all the rules and can act as a basis for this vector space. So we've got A mu, del mu from that vector space. I can find B mu, del mu from this vector space. And they're different vectors. They can't be compared. They can't be measured in any way. They can't be related. They can't be added, because when I add vectors, I can only add vectors together that live in the same vector space. And this vector lives in that one, and this vector lives in that one. You can't add. You'll never be able to do B mu del mu plus A mu del mu. It seems like you should be able to do something with this, right? Del mu and del mu. Why can't we do del mu b mu plus a mu? Why can't we do that? It's because these are vectors of a vector space here. These guys are vectors of that vector space, and these guys are vectors of that vector space. We actually need another label, right? We need some kind of little label, maybe a little p up here, or a little r for this one, and a little s for that one, or something like that. These are not, just because they're differential operators acting on functions, the thing that distinguishes them is that they're the derivatives taken at this point or at that point. So in some sense, you might write b mu del mu at r, b or a mu del mu at s, something like that, to show that these things are not in the same vector space, or they're not the same differential. In some sense, they're not even the same differential operator, because it's talking about derivatives of these functions taken at this point, and this would be derivatives of these functions taken at that point, and that's just going to be a different answer. So you can't add these things together. So the architecture, as I've been calling it, of space-time is that every single point, and these four that I've drawn, and all of the ones that are in between, and all of the ones that are not shown here, like the ones that are over here, and the ones that are over here, and the ones that happened a long time ago in the past, and the ones that will happen a long time to come in the future, every single one has their own vector space. And then, as a reminder, once I say you have a vector space, then you know immediately you have all of the other things. You have a dual space, you have all these different tensor product spaces, you have millions of, a countable infinity of those. You have an uncountable infinity of points in the space-time, but you have a countable infinity of tensor product spaces, and they all exist at each point, All right, so now how can we make sense of all this? We now have to, so we have so much stuff, we have to understand not just what's going on in a single vector space, now we have to understand what's going on in the vector spaces at every single point in the entire space-time, this uncountable infinity of vector spaces. So how are we going to do that? So it actually starts from, and you'll see this, I'll be redrawing this picture over and over again, I'm sure, but I don't know why I pick x1 and x2 I think that's just two spatial coordinates, and nice, easy to visualize, and then you understand there's time and a missing third spatial coordinate. But let's just, considering just say these 4 points to represent all the points. These 4 points will represent all the points in space-time. So P, Q, R, S, something like that. I now need to talk not just about, if I'm going to talk about space-time and this vast architecture, I'm no longer going to talk about a single vector space. I've got to talk about them all. So how can I talk about all these vector spaces in one fell swoop? Well, before I said, okay, we're going to establish a vector space V, we're going to give it a basis. We're going to give it a basis E mu. Well, I want to establish a basis not just for one vector space, but for every one all at once. And the way I'm doing that is because I've got a coordinate system out here, I'm going to speculate, well, we can imagine functions on the coordinate system, right? We can imagine these things, and we can certainly imagine taking derivatives of these things, right? Partial derivatives. We can imagine doing that. So what I'm going to do is I'm going to make the basis, I'm going to use this and this realization of a four-dimensional vector space, and I'm going to make that the basis choice. And now I know that no matter what point I'm at, the basis is just going to be the differential operators that in principle could act on functions on the space-time. That, if I had functions on the space-time, I could take these derivatives, and those derivatives will satisfy my concept of having a basis for the vector space. and it puts a basis at every point. I know that the basis at S will be these derivatives evaluated at S. The basis at Q will be these derivatives evaluated at Q. And I don't even have to have a function to do this conversation because I'm creating operators, differential operators, that someday when I have a function I can use them. So what this does is it allows me, the reason we use this is it allows me to establish a basis in every one of the infinite number of vector spaces that we have created. I can, with one fell swoop, I can create a basis for every single one of them. And the basis will make some sense based on the coordinate systems that we've created. Once I've created the coordinate system, I can create this basis. And all the basis is it's just sitting there sort of creating vectors where each vector is going to be expressed like this, right? In this, in say S, say well, I guess that would be in this vector space V sub S. You know, a typical vector would be A mu del mu, and a typical vector in this vector space is this differential operator. We could even call it, say, L. And as such, it is its own entity, a differential operator. But in principle, if a function did roll around, this differential operator could act on the function, and it would give me A mu del mu F, where I evaluate these derivatives, multiply by these constants, evaluate the whole thing at S, and then I get a real number, right? So these differential operators take functions and when evaluated at a point will give you numbers. So this I can do or not do if I have a function, but the linear operator exists and is a vector in this abstract definition that we have because it behaves and it obeys those properties of a vector space and it lives at S. The distinction at P, it's the same story, right? But my evaluation is now at P, right? So that's why this thing is the basis of all of our vector spaces. And it's a special type of basis. It's called the coordinate basis, right? Now, so that's one way to create a basis for every one of these infinities of vector spaces. So what about establishing, what about the dual? What about V star? All right, so let's have a look at that. Let's see, I don't need to erase anything, I'll just sort of move it. So we've got V and its basis del mu. So V star, well, what is V star? What is the dual? The dual is a set of maps that take vectors from V and give you real numbers. So I need something that'll take a differential operator and give me a real number, right? So I'm looking for an object that takes a differential operator and yields a real number. And we call that object dx, right? dx. And dx, it's going to be the thing that, the reason we choose it is it actually looks kind of like the way it should, right? dx 0 times dx 0 should be 1, right? dx mu dx nu should equal delta nu mu, like that. And so this guy, that is the basis of the dual space. So where the differential operator del is the basis of the vector space, the straight up differential is the basis of the dual space. And once you have that, then you can create your arbitrary tensors, right? An element of V cross, well, and I should start putting little S's there because I want everybody to remember that this only exists at one point in space-time. But say an element of this particular tensor product space, right? That an element of that might be written like this. Say delta, right? So that's a basis vector of the vector space at S, a basis vector of the vector space at S, and a basis vector of the covector space at S. Now notice, keeping track of the little s is getting more and more problematic, right? Because now, where am I going to squeeze the s? Am I going to put it on this side, right, maybe? Or if I put it up, it kind of looks like an index. So everything becomes very contextual. The fact is when I write something like this down, very, very, very rarely am I talking about it at a single point. Very rarely am I talking about it at a point x. I'm actually talking about it at every point. I'm talking, when I write down this particular tensor, I'm actually going to each point in the space-time, and each point in the space-time has its own little vector space universe that includes a vector space, a vector space, a covector space, and then all of the attendant tensor product spaces. And I'm going to each tensor product space, and I'm pulling out that particular tensor, and I'm talking about it throughout the entire space-time. And this introduces the notion of a vector field. Or, in the specific example I gave, was a tensor field. Right? I'm not talking about it anymore at one point. I'm talking about it everywhere. And once I talk about it everywhere, I don't need these little s's anymore. I can just go back to saying v, but we understand I'm talking about it at every place. And because these derivatives exist at every place, every point has its own set of linear operators, bases vectors. This becomes a prescription of extracting a tensor at every point in space-time. And the same, of course, I've been using the example as tensors, but the same it's really true for vectors as well. This is a prescription now of pulling out a vector at every point in space-time as far as this goes. But what about this thing? What about the components? Well, the components, they have to be functions of space-time also. Once I know if the component itself is a function of space-time, then I can now say that this function of space-time attached to basis vectors that exist at every point in space-time forms a vector at every point in space-time, right? This point x mu has that, there's a vector in its little vector space that has this function of x mu as a component and the standard coordinate basis, and that this is a vector located at x mu in this little let's say that this location of P was x mu. In this vector space block at P and x mu, this is the vector that I'm interested in. But what's nice is once I have this component as a function of coordinates, once the component is a function of the coordinates, I can then talk about, oh, well, what about Q? Well, Q also has a x mu, del mu, like that, right? But in this case, x mu is evaluated at Q. In fact, I could write a mu at Q of del mu, right? I just need the coordinates of the point Q, and I insert those coordinates into this function A, and I get the components relative to the basis at Q of a vector at Q. So if I define a mu x mu, where this is a function, where these components are a function of space-time, and I know that I'm using the canonical basis of the coordinate basis system, this structure gives me a vector in every single vector space at every single point in space-time. Now, the price I pay is the components become functions of space-time, and the vector basis is no longer some abstract notion of E mu. The vector basis actually have to be these differential operators relative to these coordinate lines. And once I've established those differential operators, I've put a basis in every single point in space-time. I've got components for every single point in space-time. So this process pulls out a single vector for every point in space-time that belongs in the vector space V at each point, right? So at each point x mu, there's a vector space V, and this formula tells me what that vector, what a single vector is. I pulled out one vector from each of those vector spaces, and I've done it all at once. So I'm no longer talking about a single vector in a single vector space. I'm now talking about an infinite number of vectors in all the vector spaces. And it's much more common to just drop all of the pretense and just assume we're talking about vector fields. So we just assume, hey, we're talking about a space-time. We're talking about points that are labeled by coordinates x mu. When I talk about a vector field a mu del mu, of course this is the coordinate basis, and a mu always means a mu as a function of space-time. Whether I explicitly put it there or not, a mu is always a function of space-time, and therefore I'm now talking about a vector that exists, or a vector field, we call it now, once it becomes a function of space-time, it becomes a field. That's really the touchstone of being a field. So a vector field is just a vector that it's a vector components that are functions of space-time, and in our case we're using the coordinate basis. And whenever I talk now about a mu del mu, I am talking about a full field of vectors, one located at this point, at this point, at this point, at this point, at that point, every single point, and the vector at this point, if that point's position is x mu, it's a x mu nu del nu, like that. And if it's at, say, this point, and remember, these are dummy, so a mu x, a nu x mu del nu. Remember, you need this to contract with that. This is just a label of a coordinate point. It's not even the same kind of index as in the other case. So this coordinate point is just the coordinate point of wherever you're interested in. But we leave it as a variable to say, hey, we're talking about one vector in every vector space. And the same is true, by the way, for tensors, right? If I have a tensor alpha, beta, gamma, delta, and it's going to clearly be del alpha tensor product, del beta tensor product, dx gamma tensor product, d x, what was this last one supposed to be? This last one was supposed to be something. Let's say this is lambda and this will be epsilon, dx epsilon, right? Where this is clearly the basis vector in the tensor product space, v dual, v dual. I'm no longer labeling these, I'm not going to bother labeling these vector spaces with points because we know this is true for every point in space-time. And this thing here, which was the point I intended to begin with, alpha, this is a real number, right? Alpha, beta, lambda, epsilon. This is just a function now of space-time. So I can now find, if I pick out a point Q, I learn its coordinates are x, say I learn if its coordinates are y, y mu. So I just stick y mu in here, and I find the components at the point Q, and I attach to it the basis vector at the point Q, and I now have a differential operator. I have the tensor sum. I have a tensor product space of differential operators that act at Q that represent this tensor object, right? And of course, in most general relativity textbooks, or at least the most that I read while I was learning the subject, they even drop all of this, and all you have is this, and you know it's a function of space-time, but they even drop that, and all they write is this, right? That's all they write. They simply write this thing here, and when you look at that thing, you need to think I'll write it again, I guess. Can't hurt to write it a million times. You need to think function of space-time, right? So it's a field, and then you need to think about its basis that they almost never show. Because there's no real need to once you understand the rules of how, oops, x epsilon. This object here, this one little tensor that you see with ordered indices and one symbol and it's representing a real number, actually you need to think about this whole structure. This part tells you it's a field, it's a function of space-time, and this part is the basis that explains how the mapping nature of it works. Okay? And the reason you can go from here to here and not look at all this stuff is, one, you know it's a field because we understand the architecture of space-time, and two, the mapping is all maintained by the index gymnastics. So if you learn your index gymnastics, you understand, you can skip all that stuff. All right, so from now on, whenever I talk about a vector space, you now understand that I'm talking about all of the vector, I'm talking about a vector field, and every vector in the vector space is actually going to be represented by a real number times the basis, but this real number is actually a real function. I shouldn't say even a real number anymore. It's a real function of space-time, and it's going to exist at all the places in space-time, and the dual space, you'll know, is represented by these basis vectors, these differentials, but everything's still a mapping, by the way. This thing here is a map that takes the basis vectors of the underlying vector space to a real number. So this thing still equals delta mu nu, just like ever. It's simply a replacement for those E mu's and E nus that we had before. We're simply replacing that. We're taking this and replacing it with these realizations. But the basic relationship has got to be the same. Otherwise, it wouldn't be a realization. If you swap these things out and you didn't get this, you would get some other structure. It'd be very similar, but the idea is that if it's a true realization, nothing really changes. Just it's almost the names of things have changed, but this gives us a bit of a mathematical foundation that allows us to sort of get into this coordinate system thing. So from now on, we're going to talk about vector fields and covector fields, because remember, a mu is a function of x, of the coordinate space, just like anything else. I should almost get rid of this mu here. And if I just write down x, you should understand that that represents four different, so what I really want is I want x, x0, x1, x2, x3. Well, these are numbers that are coordinates, right? So I'm going to try from now on just to write x, and it represents that. If I throw in a subscript here, people get confused because they think that a coordinate is not contravariant, right? It's not a vector, so it's not contravariant or covariant, but that is standard notation. But it's also standard to drop it completely and just leave it with an x. Okay, so that was our second run through of the architecture of space-time. And our next, we'll add another element to it all in our next lecture.